In 1895, a young 16-year-old envisioned a scenario that would ultimately revolutionize our understanding of the universe. This boy, Albert Einstein, imagined chasing a beam of light. This simple yet profound thought was a stepping stone to what would become one of the most groundbreaking theories in the realm of physics, the theory of relativity. To appreciate Einstein's contribution, we must first revisit the works of Sir Isaac Newton, a classical physicist who, in 1687, published Mathematical Principles of Natural Philosophy. Newton's work, particularly his 3 laws of motion and the law of gravity, laid the foundations for classical mechanics. He was intrigued by the fall of an apple, which led him to ponder the universal nature of gravity. According to Newton, every object in the universe exerts a force of attraction on another, an idea that explained why we don't float off the Earth, and why celestial bodies like the moon orbit our planet. Yet Newton's theory had gaps. It didn't explain the source of gravity or certain anomalies, like the peculiarities in Mercury's orbit. Enter Albert Einstein, who in 1915 presented his theory of general relativity, a groundbreaking perspective on gravity. This theory filled the gaps left by Newton, addressing questions that had baffled scientists for centuries, including the nuances of Mercury's orbit. But the journey to this theory began a decade earlier, in 1905, when Einstein published his theory of special relativity, focusing on the speed of light and motion in non-accelerating frames. However, this theory faltered in scenarios involving gravity or acceleration. Einstein's breakthrough came in 1907, while contemplating a falling window washer. He realized that in free fall, one does not feel the ground's resistance, a realization that led him to the equivalence principle. This principle posited that an object accelerating in the absence of gravity is indistinguishable from an object at rest, but influenced by gravity. Einstein didn't stop there. He visualized a room in a spacecraft accelerating upward at the same rate as the gravitational pull on Earth. An observer inside this room would be unable to differentiate between the spaceship and being on Earth's surface, a phenomenon that further reinforced the equivalence principle. This insight was crucial in integrating his theory of special relativity with the concept of gravity. The real game-changer came when Einstein pondered a laser beam in a room, both on Earth and in a spacecraft. He deduced that if the beam appeared to bend in the accelerating spacecraft, it must also be bending due to gravity on Earth. This bending of light led him to a profound realization: the presence of matter and energy curves space. He hypothesized that this curvature of space, or spacetime, is what we perceive as gravity. This idea was elegantly illustrated using a trampoline analogy. Imagine a heavy object on a trampoline causing it to sink. Nearby objects will naturally move towards it. Similarly, the sun's mass curves spacetime, causing Earth and other planets to orbit it. Einstein's theory thus proposed that gravity is not a force acting at a distance, as Newton suggested, but a curvature of spacetime caused by mass and energy. Another revolutionary aspect of Einstein's theory was its implication on time. According to special relativity, the speed of light is constant regardless of the observer's motion. But when considering gravity, the path of light can get warped, affecting the time it takes for light to travel. This warping of spacetime implies that time moves slower near massive objects and faster away from them, a phenomenon known as gravitational time dilation. Einstein's ideas, initially met with skepticism, gained credence in 1919 when astronomer Sir Arthur Eddington conducted an experiment during a solar eclipse. He observed that starlight passing close to the sun bent exactly as general relativity predicted, validating Einstein's theory. This phenomenon, known as gravitational lensing, was a pivotal moment that cemented Einstein's status as one of the greatest minds in science. The implications of Einstein's theory of general relativity are profound and far-reaching. It not only advanced our understanding of the cosmos, but also paved the way for technologies like GPS, which relies on both special and general relativity. Today, a century later, the predictions made by Einstein continue to be validated through observations and experiments, solidifying his legacy as a visionary who fundamentally transformed our understanding of the universe. His journey from a simple thought experiment to a theory that challenged and expanded our cosmic perspective serves as a testament to the power of human curiosity and imagination.